Hello, my name is Caleb Reister, and today I'm going to talk about hardware security. So we'll start with a brief introduction. There are a variety of problems. The ones I'll focus on today are counterfeit chips and malicious hardware and software in embedded systems. These are fields that electrical engineers often don't think of, but I believe they should. So, there are a few solutions to these problems that have been researched. I will focus first on identifying chips, then on testing them, and then on the continuous monitoring of these chips. So, the counterfeit chips are actually a major problem. Um, this can be a variety of different activities. It can involve selling old chips as new, so removing them from a board and then cleaning them up and reselling them. Or out of tolerance chips that were supposed to be destroyed are somehow kept and then marketed as within tolerance. And then there have also been faked safety certifications. So, just to give you an idea of the problem, counterfeit memory chips in a missile defense system for the U.S. Air Force cost $2.7 million to replace. This was in like 2008, I believe. So, a major problem here is that businesses are often afraid to report that their hardware may contain counterfeit chips due to the publicity. And these components have been found in various places, everywhere from consumer devices to military aircraft. These are actually two aircraft. This is a C-17. Let's see. Oh, there it is. So this is a C-17, and this is an F-16. There have been both planes, some of them have had counterfeit chips in them. And as you can imagine, this can be a very large problem for defense technology, but also anything safety critical. So, passenger aircraft and medical devices and you name it. So, there are some methods of mitigating counterfeits that haven't caught on a large scale yet, but they are definitely promising. So, the militaries are often the ones who discover these issues, and that's mainly because of their extremely thorough testing and their close monitoring of the supply chain. But that is extremely expensive and not practical in a commercial setting. So, we need better and cheaper ways to look for counterfeit chips. And so the areas of research are, there's actually been an idea to use plant DNA that's placed in ink or possibly on silicon, though that hasn't worked yet. And this method works by starting with a botanical DNA sequence and then scrambling code that contains information about the part, and then synthesizing the DNA and mixing it with ink. And it does work, but like I said, it doesn't work with semiconductors yet. So you can't do this inside a chip. It would have to be on the outer package. And then there have also been there's been research on doing tiny encrypted QR codes, and the idea is that these can embed all of the important information about a chip. And they would be, since they're encrypted, they would be extremely difficult to replicate correctly. So, perhaps a much more scary problem is that there can actually be targeted hardware attacks. These have actually happened before, or more on the software in this hardware, but basically, universities have proven that a few thousand transistors can compromise the security of a chip. For instance, by changing a process ID that is stored in hardware of some malicious code and giving it access to steal information. Um, and there actually are situations in which governments could be motivated to do this kind of attack. The biggest example I can think of is Stuxnet, which was a worm, a computer worm, used to take over. It was used to take over Iranian nuclear facility control systems. It was in the Natanz nuclear facility. Anyways, so, and it becomes much larger as soon as you connect devices to the internet. And today, that includes medical systems, automotive systems, and industrial control systems, which all most likely have insufficient security, and it's been tested on multiple occasions. And one example of this is Internet of Things devices can and have been used to launch massive DDoS attacks, which distributed denial of service. As more devices are added to the internet with insufficient security, this becomes a larger and larger problem. So there are some solutions. Let's see. Well, first I'll say what's not a solution, and that is that you can't really do production line testing. The reason is that software and hardware, malicious software and hardware, will often remain dormant for years or months. And it's intended to be undetectable. This, again, is what Stuxnet did, which, like I said, that's software, but it works in a very similar way to how a hardware attack would work. And so production line testing is not practical since the malicious hardware or software will likely be dormant. And you can take apart a sample of the chips and look for malicious hardware, but that's difficult to find a few transistors in billions. So there are several other ideas. First, there's split manufacturing. This would work for malicious hardware added in foundries. But it involves building different parts of a chip in different locations and splitting the intellectual property so that basically it can be... Oh, how should I explain this? You split the intellectual property so that one foundry does not have enough information to solve the problem or to add the malicious content. And let's see here. But there's a different approach for handling hardware at the design stage. And I'll show you here. This picture is of a chip that was manufactured in multiple locations. So first it was at Global Foundries, which was in either China or Taiwan, and then IBM in the United States, and then this part was done at Stanford. And it contained some identification. This RRAM is resistive RAM. It was for identification. So the other approach is to fingerprint the hardware, which basically means you watch side channel outputs, which this is actually a method used for attacking hardware. But anyways, you can heavily test a handful of characteristics like power consumption, temperature, and electromagnetic emissions, and characterize the chip, and then you dismantle the samples to verify them. And then you add hardware to your circuit, and for systems such as industrial or medical controls, this could actually be a viable option since the load is generally continuous and fairly constant. Um, but it may not be able to detect very subtle changes, which could be problematic. Again, that comes to a few transistors within billions. And it can also be used to watch for software behaviors. Generally, malware will have a different power signature than the correctly operating software. So, just as an example, another example here, adding air checking and redundancy can actually improve the hardware security. So what you have here is an output predictor. It basically takes a shortcut, and it wouldn't necessarily give you the output you want, but it could give you something related to it, and then it would run through some checking hardware and raise an error. And, for instance, notify the operator of the problem. So, in conclusion, I'd just like to say that while some of these consequences and situations seem really far-fetched, the risks are real, and multiple universities and government agencies have proven that especially industrial technology and medical technology are susceptible to attack. And I would like to encourage you to consider the ethics of what you're working on as an engineer. And consider, well, what could this be used for? And, oh, I don't know how that got there. Dr. Aboy, not funny! And then here are my sources. So, quite a few. I have 12 sources, so. Other than that, thank you. And goodbye.